Good afternoon. It's a pleasure to welcome back Professor Jan Allebach to the University of Delaware. He received his bachelor's in electrical engineering from UD in 1972. As we will see, Jan learned many useful skills at UD, in addition to electrical engineering, as we will see. He then joined the graduate program at Princeton, where he received a PhD working with Beauty Liu. And it was a very special time. A lot of giants in signal processing that graduated around the same time that Jan was at Princeton. In 1976, Pete Water recruited Jan into the ECE faculty at Delaware, where he stayed until 1983, when he took a very extended leave of absence from UD. He actually joined Purdue University, where he is now the Hewlett-Packard Professor of Electrical and Computer Engineering. He leads an outstanding research group in electronic imaging, electronic printing, signal processing. His research has been licensed by industry and can be found in products that have sold hundreds of millions of units worldwide. Professor Allebach is a fellow of the IEEE. He's a fellow of the Society for Imaging Science and Technology and fellow of the SPIE. He is the recipient of many teaching and research awards at Purdue. Last year, he was elected member of the National Academy of Engineering. So please join me in welcoming Jan back to the chalkboard at UD.
Very nice introduction, and thank you all for being here for my presentation. It's indeed wonderful to be back on campus. It's been really too long. Actually, those of you who are really sharp-eyed, you may notice that, I'm not on the mic yet. May notice that I changed the title from 2,000-year-old technology to 1,000-year-old technology. I actually didn't have the number quite right. I'm never very good with numbers, so in any case. But I also, this is a picture of the Purdue campus. I wanted to, refresh Gonzalo's memory. And we also have bricks. In fact, we have an award called the One Brick Higher Award, because one of the buildings that had been just built, this is way before my time or anybody else's, burned down the day after it was dedicated. And so the president vowed the next day, we will rebuild this building and we'll rebuild it one brick higher. So they created the One Brick Higher Award. So anyway, what I want to talk about today is what is printing, and then I want to talk a little bit about printing and communication. Over the years, I've done a lot of thinking about why printing is what it is and how people use it, what its impact has been. We'll talk a little bit about why printing is still important. Then, because this is Alumni Day and I'm an alum, I thought I should be a little bit autobiographical, so I'm going to talk about how I became interested in printing. And then one of our major impact areas is digital halftoning. So I'm going to take a little detour and talk about that in some detail. Then to give you a little bit bigger picture of what we do at Purdue in our lab, what else we've done, but mostly all related to printing. And then finally at the end, I'm going to talk a little bit about some of the new things in digital printing. And so that's quite an agenda. I may have to speed up a little bit to get through before we run out of time, but bear with me there. Okay, so what is printing? Okay, and I had some interesting visits with people here this morning who do quite a bit of printing, and so I'm interested to get your impressions of this. I thought about this a bit. So I would like to say that it's the placement of a soft deformable material on a substrate or medium. Materials could include liquid like ink, hot melt plastic, powder, toner is a good example if you use a laser printer. The substrate could be flexible or rigid, cut sheet or roll. Examples would be paper, cardboard, plastics, and metal. The materials can be placed in multiple layers, and this has always been the case with color printing, but of course it's become even more true more recently with 3D printing and something I'll talk about, which is called 2.5D printing. After the material is placed on the substrate, there can be a variety of finishing processes: cutting, curing, drying, trimming, so forth and so on. For 3D printing, removal of undeveloped material can be a very important aspect. So you can create voids by taking out the part that you didn't want to have become part of the permanent structure. The placement of the material is characterized by a specific pattern or shape, and of course, when we talk about digital halftoning, that's the pattern we'll be talking about there. And then finally, this mechanism is designed in such a way that the process is reproducible, and that's a really critical aspect of what people mean by printing. It has to be reproducible. You have to be able to do it again. So here's an example, an early example, and the question is this printing? Well, the substrate is rock. The material, various dyes or colorants. The pattern is defined by the placement of those materials, but it's not reproducible. That's it. It's never going to be done again unless it was copied in some way by some other technology. So this is not printing. Now, this is the one where I got the 2000, and when I actually looked at my notes, I realized that it doesn't go back that far. This is a wood block used to print the Diamond Sutra in China, and I've read on the web that this is the oldest known book. And so the substrate, again, would have been paper. They would have used this wood block to make an impression on paper using some kind of ink. The pattern is defined by the cuts in the wood block. It's very reproducible. I can keep stamping more copies of that material. So this is printing. Okay, now why is printing important? Well, now we're going to get into this aspect of communication. So I like to think of printing as the first means of personalized broadcast communication. So both those words are very important. There were two revolutions. The first revolution had two parts. Part one was printing as a means of paper-based broadcast communication. Note the word personalized is missing there. Part two was radio and television, where this is double E, right? So we all know about that. That's a means of electronic broadcast communication. Note the word personalized is not there. And then finally, we go to the second revolution. So part one, printing was a means of paper-based personalized broadcast communication. Part two, the internet, is a means of electronic personalized broadcast communication. So now let me just give you just a little more detail on this. So before 1450, we could have oral communications. I could talk to Gonzalo, he could talk to me, as we did in his office this morning. We could have an oral presentation such as we're having now. I'm giving a presentation to a group of people in the room. Or we could have handwritten material, such as this gorgeous folio from the Book of Kells. And by the way, my first house here in Newark, my house when I lived here in Newark on the faculty was on very close to Kells Avenue, where the Kells Press lived or was located. So that's what happened. That's how communication was done before 1450. In 1450, Gutenberg invented his press. Now, before that, we had to have paper. So paper-making mills had been established in Catalonia, which many of you know is a part of Spain, in 1238. Then Gutenberg invented his movable type press in 1450, and the impact of that, I think, is amazing. In 50 years, more than 9 million books were in circulation. Later, and this is getting into some of the technical details that I won't have too much time to talk about, but lithography was invented in 1799, and then the notion or the principle of the offset press, which is the dominant commercial printing technology, even really today, was developed in the early 1900s. Okay, so now we're on to the part two of the first revolution, and this was electronic broadcast communication. So radio was invented around 1900. The KDKA went on the air in 1920. We had television. There's debate about who did that first, but in any case, the first commercial broadcast was in the 1920s. And here's a picture of Tesla demonstrating wireless transmission in 1891. So now we're finished with the first revolution. So this is broadcast communication in paper form and electronic. But the point is, most people didn't have a printing press. Most people didn't have a radio station. So if I wanted to send something to a group of people, there was no easy way to do that. So then we move on to the second revolution, which is all about personal broadcast communication. And print, again, led the way in the 1980s, right around the time I was here and then left to go to Purdue on my extended leave. Apple introduced the Macintosh PC. HP introduced the LaserJet printer. Adobe introduced PostScript, which is a page description language that tells us how the information should be laid out on the page. And then we needed graphical tools to create those documents, and the first one was PageMaker, which was created by Aldous in 1985. So all that stuff happened very, very quickly. And so that was the second revolution. Now anybody who had a personal computer could create documents that looked as though they had been published or printed by a high-end printer. So then the second revolution, let me turn this off. I think I'm getting a little feedback here. The second revolution of personal communication will be electronic, and I think you can probably guess where we're going to go with this. So this is the internet and the World Wide Web. So we have email, we have blogs, Twitter, wiki, social networks, Instagrams, on and on and on. So that's what we all do today, or at least many people. And so that sort of completes the story, except for one last piece, which is this concept of closing the loop so that I can take printed documents and which are generated by going from, I call it electrons to print, and then go back from print to electrons. So here's an example of some work that we did in our lab a few years ago where we modulated the borders of the form here in such a way that we could actually scan this document and extract metadata from the way in which that modulation is performed. And that data could authenticate the document, say something about when it was printed, things of that sort. So that's the story about printing and communication. Now, well, why is printing still important? Imaging was named one of the top 20 inventions of the 20th century by NAE. Paper has a lot of nice features to it that people still like. It's a big business. And commercial printing is really still the biggest part of it, and we'll talk more about that because that's where a lot of the new opportunities are. But printing is changing. It really is changing. Nobody prints as much as they used to. It used to be we had filing cabinets with paper in them. You may still have some, but I bet you don't put too much in filing cabinets anymore. Printing has become more of a graphical user interface. We look at it, we read it, and then we recycle it. And most of the future growth is being seen at the higher end, and then in this new area, which I'll talk a little bit about, which is fabrication. Okay, now printing is interesting because it's very complicated. I'm not going to go into any of the details here, but there's inkjet processes, there's laser, electrophotographic printing, there's a lot of parts. When we look inside and see the image processing, which is the part that I really do, there are many, many steps to that process, and I'm not going to go through those either in detail, but just to show you that it is rather complex, and it's also rather demanding. Putting color on paper is inherently a messy process. Paper is a very poorly controlled substance, and at the price points that these systems operate, we have to accept a lot of variability in their performance. So for example, these are inkjet patterns. My pointer died on me, so I have to use this cursor. But here you can see that the dots are well defined, but unfortunately they're not consistently placed. This is a more interesting example. We have a local binary pattern here that we're printing, and we print it 4 times, and yet you can see that there's tremendous difference among these 4 different repetitions. So if I'm designing an imaging algorithm, in particular a half-toning algorithm, I have to understand those differences and account for those in the model that I use for the half-toning algorithm. Printing consumes massive amounts of data. So a single page is 135 megabits. And if we're going to print 100 pages per minute, we're talking 225 megabytes per second. That's a significant amount of bandwidth. The marketplace pressure is really intense. Printers are basically cheap. And there's this constant demand to make them faster, add more features, higher quality. And the final thing is Moore's law doesn't apply to paper, colorant, and the human viewer. I can make these things, the insides of these things, smaller and smaller all the time, but I'm still going to read a piece of paper of a certain size, and I have to have a mechanism that can produce that. Okay, so now we're on, just to see where we are. The next topic here is how I actually became interested in printing, and then we'll talk about digital halftoning. So I actually became interested in photography as a high school student. I had, for those of you who are old like me, I had a Canon FT film-based single lens reflex camera, which I still have. I had a dark room in my basement. My father had a dark room, and I found the stuff on the attic and drug it down and said, "What's this?" and I set it up again. I printed black and white and developed 35 millimeter slides using the Kodak E4 process, which has like 12 steps, and you have to maintain control within 1 Celsius of the temperature for the temperature. So it's a challenging thing. This is a photo that I took of a wildflower called bloodroot in Skippack, Pennsylvania, which is not far from here where I grew up. Then, as an undergraduate at UD, 1968 to 1972, I had no idea that EE had anything to do with imaging. As I was talking with Tom McCormick, who's an alum who happened to have me as a professor in the digital signal processing course at the sophomore level, I said, the problem with that class was there were no applications to talk about. JPL was doing things with NASA, but there was really very little. So now when I teach DSP, I can just get this out and say, how many people have one of these? How many people have a digital camera? Everybody's got one. And so, it really frames the conversation very quickly. And, as a matter of fact, when I applied to graduate school, and I laugh about this now, I said I wanted to do computers, communications, and controls. Well, I didn't leave much out, did I? So, of course, it was ridiculous. But when I got to Princeton, my major professor was very interested in Fourier optics, Fourier as in the Fourier transform. This was a hot new thing at that time. A professor at Stanford, Joe Goodman, had published a book on this. And so I got interested in this, and the first part of my dissertation was digital holography. Now, you may say, what's that have to do with printing? Well, what it has to do with printing is that the goal was to design patterns, which it's a little hard to see here, but that's a binary pattern. It's either 0 or 1 at every point. And if I shine a beam of coherent illumination through that and look at the back focal plane of a thin lens or just go far enough away, I get a pattern that looks like this, which in the application that we were talking about was for target recognition, match filtering for target recognition. So the key aspects of this was that it was binary signal design, and secondly, that it used Fourier analysis for its basis. So then that was the first half of my dissertation, and at some point, my major professor went away to Japan for a month, I think. And so I didn't have to meet with him every week. And every week it was always a challenge to come up with something new to show him what I had done, and so forth and so on. And so while he was gone, I had the freedom to just go to the library and do some reading. So I discovered this paper called Fourier Spectrum of Halftone Images. And the halftone process is extremely nonlinear, and the notion that you could use Fourier analysis to analyze something like that, I thought was fascinating. And so when he came back, I had some ideas of what we could do with this, and that's how I got started in digital halftoning. Now, as Gonzalo mentioned when he introduced me, I actually came back here after I finished graduate school, and there is actually a significant Delaware connection to the halftoning. I managed to get Gonzalo interested in it, and so we published another paper, which I won't talk in detail about what this involved, but basically we started a collaboration, and and did a few things in this area as well. That's the part one. The part two has to do with Daniel Lau, who's sitting right over there. He was an undergrad at Purdue, and I had him in a senior DSP course. And that semester, we did a project, which interestingly was digital halftoning. And so that got Daniel interested in this area. He's gone on and done many other things since. But this is actually a paper that he published, which I think was a very seminal piece of work. And Gonzalo was also a co-author. And this is actually a slide from a presentation that I gave. It was intended to be a little bit tongue-in-cheek. The topic of the talk was really green halftoning, as in reducing ink usage and making it more environmentally friendly. But I went through first and talked about all these aspects of green halftoning, and so I used this slide to talk about green noise halftoning. So anyway, so that's the Delaware connection, and this is, I mean, there's much more I could talk about. Gonzalo just gave me a copy of the second edition of his book with Daniel Lau. So that's been a major activity here. And going back to this slide, I found out today that this is really in some ways very similar to some imaging work that Gonzalo is doing called coded aperture imaging. So again, binary signal design. So now let's talk about digital halftoning. I've alluded to it many times, so it's time to actually tell you what it is. So it's the process of rendering a continuous tone image with a device that's capable of generating only 2 or a few levels of gray. And the way we do this is by creating these high-frequency binary patterns. And at the appropriate viewing distance, the viewer doesn't resolve those dots, and instead they see some continuous pattern of gray. Now, I have to warn you, I'm going to show you a few halftone images in this talk, not a lot. And you may notice, depending on where you are, that this one seems to have some sort of banding structure in it. That's because the projector doesn't have enough resolution to actually reproduce it. So this is actually an undersampling or aliasing artifact. This one over here, of course, is fine. So you folks in the very back of the room are probably getting the best impression here of what I want to show. So now, nobody's interested in looking at these patches of constant tone. We have to be able to modulate this. And so we have to be able to create detail. And so we do that by local modulation of the texture. And so we can get something like what you see here. And now there are basically 4 broad categories of algorithms for doing this. And again, I'm not going to go into the details of these. I'm just going to talk about 2 of them. But this screening process is the classic process that's used for commercial offset printing. And this is a dispersed dot version of that. Then there's something called air diffusion, which we'll talk about a little bit more. And then finally, there's this iterative method, which was something that we developed, first for digital holography, then for halftoning. And as you can see, hopefully, as I go from left to right, the visual quality increases, but also the computational cost increases. So, and then now I'm going to talk to you a little bit about these algorithms to give you some idea how they work. So first of all, there's a general framework to think about how these algorithms work. And I'll just describe this in briefly. At the heart of this, we have something we call the rendering algorithm. And I'll describe what that looks like for 2 examples. We sometimes have training data to tell the algorithm how to determine what its parameters should be. We need to have some kind of a quality metric so we can look at the output and say, yes, this is a good result, this is not a good result. And that quality metric ought to at least know something about the human visual system, because in the end, it's all about what the human viewer sees. It can also be helpful. You remember the slide where I showed the 4 different instances of the same binary pattern that look very different. It can be very helpful to have a model for the rendering device. And so those things can feed into this quality metric, and then that can drive a search strategy that guides this rendering algorithm. It can either train parameters, or it can actually literally determine the bitmap, the halftone image. Sometimes there are constraints. Of course, a big one is that halftone images, at least in a very simple instantiation, are either 0 or 1, that is binary, colorant at a pixel or no colorant at a pixel. So this is the big picture that describes a framework for thinking about the work we've done on halftoning. Okay, now this is the first algorithm that I'm going to describe. And this is called direct binary search. It's really a very simple concept. Up here in the upper right corner, we have this block diagram again, and I put red around the part that we're going to focus on here. So first of all, we have a continuous tone image. This is what we want to reproduce, but we can only do binary images, such as shown here on the lower left. Again, as I mentioned, what matters is the human viewer. So we have a model for the human visual system. It's actually a rather simple model of what we call point spread function. And so we process this continuous tone original with the point spread function, and we get something that we call the perceived original image. So that's what the human viewer sees. There's no reason to produce anything better than what the human viewer sees. That would be unnecessary cost. So then we do the same thing with our halftone algorithm, and we get the perceived halftone image. And now here we could do lots of different things, but in this particular case, we look at the difference between the two and just integrate that, and that gives us a single number, which is a measure of the difference or the error. And then we drive that back to guide this process of searching for the best halftone image. So now we'll talk about how we do that search. This is a heuristic, which means it's just an ad hoc idea for doing it. There's no real theory behind this. I mean, there's a lot of theory behind how it actually works and why it can be made efficient, which I won't talk about. But in any case, we scan through the halftone image pixel by pixel, and at some particular location, like right there, we have a local neighborhood. We consider toggling the center value or swapping any pixel that has a different state from its neighbors with the center value. We look at all those options. In this case, there's only 4 for this local neighborhood, and we keep the one that reduced the error the most. If none of them reduce the error, we just leave it the way it is and go on. And then we scan, we go to the next, my cursor keeps hiding. We go to the next pixel on that line, go to the next line. We go through the whole image, that's one iteration. We go back and do it again, that's another iteration. As we do this, we accept fewer and fewer changes, and eventually no changes are accepted. So when we do that, we've converged to what we would call a local minimum of the algorithm, and this shows an example. Here is the initial randomly half-toned image, 1 iteration, 2, 4, 6, and then finally after 8 iterations, we have a pretty high-quality reproduction. Now, I actually forgot to mention that there's 2 very specific changes here. One is the toggle, where I change this center state. It turns out that's a pretty drastic change. The other is a swap, where, for example, I take this pixel and move it to that location. And one of the innovations in terms of what we've done, and I don't know how well this will show up, but if we do toggles only, we get a relatively noisy result because we weren't able to refine the texture locally as well as we'd like to, whereas if we do the swap then toggles, we get a much better result. Now, you may think about this a minute, especially if you were, those of you in the room who are engineers, and say, well, you know, this sounds like an awful lot of computation. Can you really put this in a $50 inkjet printer? I don't think so. It actually, I won't go into details, but there are manufacturers now who are thinking about doing this, but it's not for low-end printers, it's for high-end printers. So this wasn't going to have any real product impact unless we could do something to make it more usable in lower cost products. And so that's where the next algorithm came in, the last algorithm we're going to talk about, which is called tone-dependent error diffusion. And again, I don't want to give you a lot of detail on error diffusion, but the basic idea of half-toning in this context is we have this, what we call the modified continuous tone image. We compare it to a threshold. If we exceed the threshold, we print a dot. If we don't print a dot. And then we look at, that's this thing here, G of MN, that's the halftone output. Then we look at the difference between that halftone output and the input. That creates an error signal. And the idea is to feed that ahead to the pixels that we've not yet made a decision about. For example, if we're scanning in raster order, row by row, and we just binarize this pixel, we could feed some error to this one, some to that one, some to that one, and some to that one. These are on the next line. And so the idea is that, for example, if I printed a 1 here and the value was supposed to be 0.6. I'm 0.4 too high in units of absorption. So what I'm going to do is subtract 0.4 from a combination of these pixels that I have not yet binarized. So if I print a dot at this location, I'm less likely to print dots at these locations. So it's a feedback mechanism, negative feedback. Okay, now what we did, and this again shows how it fits in the framework. I'm not going to go into the details of that, but our novelty here was to say, well, we have this wonderful algorithm called direct binary search, which still today I think is the best quality dispersed dot halftoning algorithm that's been reported. Maybe if we made some parameters of this error diffusion algorithm depend on the local tone level, we could train it to mimic DBS. And so the parameters, what we did was we said, let's make these weights by which we distribute to these neighboring pixels, let's make those depend on the gray value of the pixel that we're trying to halftone. And then I'm not going to talk about in details, but we also made the threshold tone dependent. So, so we have a cost function here. Now what we're doing is we're looking at DBS halftone. We have a constant tone patch, that's the training data. We generate a DBS halftone of it. Maybe we call that the training data. We take the same constant value, feed it to tone dependent error diffusion, and for convenience, we'll do this analysis in the Fourier domain. We compute spectra of these two halftone patches, look at their difference, appropriately normalized, and then we do a search for that gray level. We do a search to find the weights, of which there are 4 in this particular case. Let me just go back again. There are 4 weights here that we're going to halftone over. So we do a search to find the values for those weights that minimize the cost function. Now, I also mentioned we also optimize the threshold, but for simplicity, let's not go into that too much. So this actually shows as a function of gray level, normalized between 0 and 1. 0 means paper white, and 1 means we put down maximum colorant. And this color codes the location to which we diffuse the errors, the amount of error that gets diffused to those locations. It should sum to 1 at every weight. I have no intuition about what's going on here, or at least not very much. It is symmetric about 0.5 because there's this property that, that the halftone textures that in the highlights, where you have fewer dots than you have paper white, should be the complement of the halftone patterns in the shadows, where you have mostly black and a few holes. So that supports the idea that these weights could be symmetric about 0.5, which is the midtone. Okay, so enough of that. The question is, how did it do? Well, this was the canonical error diffusion algorithm, and of course there's been lots of work that's been done to try to improve this, and I won't go into that, but it has some well-known artifacts. This is actually a startup problem here, so we don't need to worry too much, but these are classic issues called worms. And so with our training, we were able to completely eliminate that and get much better texture. And then the next slide is the one that I think is especially interesting, that if we compare this on the left, tone-dependent error diffusion, to the one we trained it to mimic, DBS, you can see that, I mean, if you looked at it microscopically, the dots aren't in the same places, but visually the quality is equivalent. And so the significant thing is that error diffusion is a one-pass algorithm. It only processes the image. We only need to have 2 lines of data stored in memory. So it's well suited for an embedded application. And when Gonzalo introduced me, he mentioned hundreds of millions of units. Well, this went into an ASIC, an application-specific integrated circuit, that is in every inkjet printer sold by HP for the last decade or so. So at one point, they were selling about 1 million printers a month. So that's where you get the total number of units that have that halftoning algorithm in it. Okay. Now, so that brings us to the next topic, which is what else have we done at Purdue in printing? So I just want to give you a little bit of a bigger picture of the things we've worked on. And there's too much here to go into detail, but first of all, we've worked with many different sponsors, mostly all to do with printing. Hewlett-Packard is the biggest one, and I'll have more to say about that on the next slide. The research has been very multidisciplinary. These are a number of my colleagues in ECE who have worked on various projects in the printing area. Also, I've had a long-term collaboration with George Chu in mechanical engineering, 2 industrial engineering professors, and then Zig Pieslow in psychology to help me understand how humans perceive image quality. So this is what we've been able to do. Now, if I just talk about HP-sponsored projects, again, I'm not going to go through this list in detail, but they span the range from low-level image rendering, which include digital half-toning, and then image quality, print quality assessment. These are tools that are used during product development and product testing. And that includes artifact. Well, artifact detection is work that we did primarily for commercial printing. I'll come back and talk about that in a little bit later. Web-based troubleshooting tools, I'll mention that in a minute. That's for customers to troubleshoot their problems. Then this one, digital photography related, you may say, well, what does that have to do with printing? And when students come in to ask about doing research for me, I say, well, everything I do has something to do with printing, but it may not be what you think. And then I'll describe this stuff up here a little bit, which is printing, as you would think of it. This here, these topics, and there's some more which I didn't include here, content creation. It's all about creating something that will encourage people to print. So, so basically, HP had activities in areas where if we can create content that will make it easier for the customer to print what they want, we'll sell more toner. We'll sell more ink cartridges. And so they were willing to support some very interesting projects, which unfortunately I won't have time to talk about today. Okay, so now I'm just going to give you, so these are just some examples of products that, just a small set of products that have our technologies, ranging from low-end inkjet printers to high-end digital presses, and I'll talk more about those in a minute. This is an early example of some work that went into the drivers of all HP inkjet printers. It was a technique called resolution synthesis, where we tried to train the algorithm to synthesize the detail in an image. Kind of a bit like your patch-based stuff that we were talking about, now that I think about it. Yeah. So, so anyway, that's that. Tone paint air diffusion, we already talked about that. The web-based print quality tools. This is something we did with the industrial engineering professors, human factors people. How do people use a web-based tool to troubleshoot their problem? What can they understand? What can they not understand about the guidelines and the tools that we give them? So these are online at hp.com for about 20 different mid-range products. Here's an example I like because it's the opposite of half-toning. It's getting rid of the half-tone pattern. So if we want to copy something and then reprint it, and it already has a half-tone pattern, we may get a beating phenomena where we get moire problems with the halftone that's in the document. So here we remove that with something called hardware-friendly descreening. This was an effort that was led by a young professor in our department, Mimi Bouton, and Charlie Bowman was also involved. I was very involved in kind of managing it, but my name didn't go on the paper. But in any case, this went into an ASIC. That's what hardware-friendly means to us. It means it's suitable for an embedded application. Okay, so finally, a few years ago, we celebrated our 20th anniversary. So this is just to give you an idea of my group. And as you can see, there's many international students, many women. I'm very proud of that. We've had, just to summarize, 30 patent applications, 50 PhDs, 15 master's theses, lots of papers, and a sizable amount of funding. So that's kept me busy over the last 20-some years. And so now we're ready to go on to the synopsis. And I promised Tom that I would put this picture in. So I've had the honor to give away 3 of my women Chinese students in marriage because their fathers could not come over from China for the wedding. And so this is one of them. This young lady, Lu Wang, also went on to have a baby. I've had, I think, maybe 6 of my women PhD students have had babies while they were doing their PhDs with me. So she had her baby last fall, and she and her husband just moved to Mountain View, and she's starting work at Google in a week or two. And he got a job with some kind of company that, he's a finance guy. He got his master's in finance from University of Chicago, so he got some job related to that. So anyway, so now the last thing is what's new in digital printing, and we don't have an awful lot of time, so I may need to go through this a little more quickly. So here's a summary list. Digital commercial printing of marketing collateral, that means brochures, requests for donations, all kinds of things we call digital assets, reports, and then books on demand. If you want to buy a book that's out of print, you get it printed on demand. Digital printing of packaging. This is huge in my opinion because, as I was saying, we don't print as much as we used to. We do more and more reading from display devices, but this came in a box. It had stuff printed on it, and that's part of the marketing. You go in the supermarket, everything's in a box. So there's a lot of opportunity there to sort of personalize that and include more information. 2.5D printing, I'll talk about that a little bit more. That's I think, a very interesting area. And then finally, we'll end up talking about functional printing. I didn't actually get a chance to put anything in here on 3D printing, and after meeting with, shoot, I've forgotten your name, this morning and seeing his 3D printing effort, I'm glad I didn't put anything in here because there's quite a lot of 3D printing going on here right now. It's some very nice activities. So anyway, but I will talk about printing as a tool for manufacturing. So this is what's driving digital to commercial print. So digital print, this slide's a few years old, but it hasn't changed that much. It's only 4% of the total pages produced. The vast bulk of pages printed in the world today is still done using analog processes. And so I like to call this the blue ocean after this popular book on blue ocean strategy, which is if you want to get into a market, you go where no one else is. You don't go in the water that's full of sharks fighting for the little bit of food there. You go where an area where no one's recognized the opportunity. So this is what people are doing, and HP actually has been very successful. Now, what do I mean by analog printing? Well, this is the printing press that we used to have at Purdue, called Heidelberg. Heidelberg's a very well-known German company. They still make print presses. You buy one of these, it's a huge investment. You use it for 20, 30, 40 years. The major idea is that there's a plate that you use that will attract ink, and then you bring that plate in contact with a blanket in this case, and then that gets transferred to paper. But you can just think of it as bringing the plate in contact with paper, and the ink gets transferred to the paper. Now, the important characteristic of this is that with that plate, it's a fixed piece of metal, you can only print one thing. Every page looks exactly the same. There's a lot of effort and a lot of expertise. In fact, here's the guy right there. That's the press operator. You can barely see him. He's a very skilled fellow, and it takes him a long time to get this press set up to print one impression, to get the inking correct and the color correct and so forth. So it takes a lot of money to use this type of device, and that means that you're going to have to print thousands of copies in order to make it economically viable. On the other hand, digital printing is basically digital publishing. Is like digital printing. I like to call it desktop publishing on steroids. You use the same software to create your document. The technologies are basically scaled up desktop printing technology. And the important thing is that this is what we call variable data printing. Every page can be different. So if I want to print a one-page document, I can print it on this device. And if Gonzalo has another page, a different document he wants to print, I can print it. If I want to print an advertisement, in fact, we've done this, personalized media communication. Purdue does this all the time. For example, they had a request that went out to former athletes. So they had a nice letter, and in the background was a picture of an athlete from whatever sport it was that person had played, swimming, football, whatever. That was the background of the paper, and then of course the letter was pretty much, it could be customized too. So that's an example of personalized marketing. And so this sort of supports this very well. You can make one impression or 1,000 or even more. Now, these per page are more expensive. So eventually, if you're going to print a lot, you go to the commercial. So now here's the analog. So here are some examples of new HP digital presses. This one is suitable for packaging. This one is inkjet, and this one you measure the output in how many feet per minute, 800 feet per minute. And so this is targeted for textbooks, very low-cost textbooks. And then finally, this one is inkjet, but it prints a very thick, viscous ink, which is UV cured, so it's good for posters and banners and the things you put on the side of the buses, that kind of stuff. So anyway, so that's where the market has gone. And interestingly, this company, this division of HP, Indigo, and also Cytex are both based in Israel. So I get to go there now twice a year and meet with those folks. So now that's one market, that's one area, and you can think about some of the digital half-toning things. We're still doing that. The next area is a little bit different, and this is actually work we did not do with HP. We did it, in fact, with a company called OSE Print Logic. And this is semantically based 2.5D detector printing. And I'm just going to give you a quick overview. The idea is to create a print which is almost flat, but has a little bit of relief structure that simulates the appearance of a desired texture. And so I'm going to actually, it's a huge audience, and I don't know how far these will get around, but I wanted to pass some samples around to show you, and I need these back again, otherwise my graduate student will never speak to me again. But anyway, I'll take this one halfway up the room here and get it started. So these are examples of relief printing done with some experimental technology that OSE has created. And so then the question is, well, how do you use this? And so we have a process whereby we can train an algorithm based on keywords to figure out what parts of the image are likely to have that particular item. And so, for example, here the keywords was leaves. And so the algorithm will figure out that, this is a fairly simple example, that this is where the leaves are. And then, we have a whole process for doing this. I won't go through the details, but I'm passing around the examples of what it looks like. And ultimately, we generate something called a height map, and then we use that to guide the actual printing, which is done by putting down multiple layers. So this is what I was talking about earlier when I talked about multiple layer printing. Okay, now, manufacturing. Why should we base manufacturing on digital printing technology? So again, I wanted to think about this a little bit for this talk. So it's scalable to high volume and high speed by leveraging the knowledge gained from commercial printing industry. It's analogous to variable data printing. Every part can be different. One of the things we're thinking about is printing pharmaceuticals on a web-to-web system. So you have pills in a row. Every pill can be personalized to the person who's supposed to receive that medication. It's also analogous to the manner in which printing is done in color, which I mentioned before, because you can build it up in multiple layers. That's key to 3D printing. It's additive rather than subtractive. So potentially you could reduce material cost, allow more complex designs because you can have that material that gets removed during the post-processing, so the inside can be open. Again, since it's digital, it's reproducible, you can make one of them or you can make 1,000 of them. So that's the potential for manufacturing and digital printing technologies. And here's a little bit of work that we're doing with my colleague George Chu actually is doing. And what was kind of interesting about this is they were using DBS to decide on the order in which nozzles are fired to place conductive material on a pattern, and what you can visually see that the one on the left here is quite jagged, and this one was just some design of the print mask order that was done by a human. And then finally, this was optimized using the same kind of search that I talked about, direct binary search. And if you look at the RMS roughness, the resistance is, that's a key thing. It's supposed to be a conductor. So the resistance has dropped a great deal. And this was the cost function he was minimizing. So anyway, so this is just one example. Here's one more example that looks at the notion of printing sensor materials. So this would be very low-cost sensors that would detect certain things in the environment. In fact, we're currently talking with our food science people about developing little test strips that you can put in food at the supermarket. The inspectors would do this to test for the presence of bacteria. And so the idea is these are arranged in a certain spatial pattern. If you do a Fourier analysis of this, and that part isn't in here actually, that's too bad, you get very different frequency patterns depending on what antigens this was exposed to. So these are some examples we're looking at. I find out today that there's some really exciting stuff going on here. Same kind of philosophy. This, unfortunately, oh no, here it is. Here it is. Okay, there's a little bit of annotation or animation. So this is a little more futuristic. What I showed you just now has already been done. This has not been done. So we're talking with our pharmacy people about creating a multi-layered drug that has sensing capability, activation capability, and active ingredients, and then an RFID locator to help manage how that drug is used. And then this is a roll-to-roll facility that has just been installed at our nanotechnology center. And that's pretty much it, I guess. Yeah, I think I'm just about almost on time. So anyway, that's my presentation. This is a photo that I took here at Delaware back in around 1970 along White Clay Creek. So thank you very much for your attention.
Jan, I have a question. In the printing of conductors that you're using the DVS, what's the cost function that you're using?
The cost, there was one that's typical, as you would think of image quality, which is this uniformity of line edges. And then there was something else related to coalescence, because the big issue is if I put a drop here and then I put another drop right next to it, this drop moves over and kind of flows into the one that I just placed, and you want to avoid that. So basically you want to put some dots down that are sort of sparsely arranged, then go back and put more dots down and so forth. So he called it the coalescence. The graduate student who did the work called it the coalescence cost function. So, yeah, thank you. Thank you. Yes, sir.
How the print quality of paper related to the quality of display something on computer screens?
Oh boy, that's an interesting question. Well, certainly print still has a little bit higher spatial resolution and a little bit higher quality for reading black text, but I don't know how much longer that's going to stay. I mean, with the Retinex display, for example, with the resolution has gotten to be so high that, and I have to say, I can't remember now what the contrast numbers are, but I think black ink on paper still has more contrast when viewed under office lighting than a typical display would have. But you know, it's more a question. You know, I mean, the more important question is when do we reach the point where it's good enough? I mean, display technology, and I think basically we're there. I think most are pretty comfortable reading from displays at this point in time. I guess from my point, there is a usability issue. I don't find it easy to flip through a document electronically nearly as much as if I have a printed version of it. I like paper myself anyway, but on the other hand, if I'm going on a trip, although I don't actually, if one were going on a trip on on a plane, you can have a whole bunch of books in your reader. You don't want to put all those books in your briefcase, and you know you need to decide ahead of time what am I going to look at. So it's an interesting trade-off. You know. Thank you.
I was just curious, when you were showing the side-by-side images, how do you determine which one is better? How do you determine when your algorithm has succeeded?
Well, we have a cost function that we're minimizing, and so we could compare on the basis of the cost function. But actually, I'll give you a better answer to that question, which is, you know, we do a lot of subjective experiments. And so I didn't show, I was almost going to show an example of something, but I took it away. But for one of our algorithms, we were very interested to know how it was performing with compared to other methods. And partly because I didn't think the difference was so obvious. So we did a subjective experiment where we had prints side by side. Subjects were asked which one looks more uniform, because that's the goal of digital halftoning, to get the most uniform appearance. I mean, you could say, well, detail rendering is important also, but in this case, we were mostly concerned about minimum grain. And so they don't know which is which. They do multiple observations of the same sample. We analyzed the data, and we were really pleased. I mean, I was amazed. I mean, our algorithm came out far better than the other two that we were comparing with. So that's the ultimate test, is to do psychophysical studies. And we do that not all the time, but we do it some of the time. Yeah. And sometimes we even parameterize the algorithms based on the results of psychophysical studies. That's a very good question. It's also very tedious. The students spend a lot of time doing that kind of thing if that's what they have to do. So.
Any other questions? Well, last question, Jen. When are you ending your
I'll have to think about that. Okay. Thank you very much.
So I don't have a mic. I'm going to try and talk loud. I hope everyone can hear me. And as evidenced by Jan's talk and all the posters and everything that were upstairs, it's really incredible to see the breadth and depth of work that's done by the UD students, faculty, and our alumni. And this is an opportunity for us to recognize some of that incredible work. So we have some awards for alumni, as well as the research posters for the students out there. So we'd like to recognize that now. And the first award is our Distinguished Achievement Award. And that is given to an alumni. I'm just going to quote what it's for, is for the notable significant contributions. It's the highest ECE award, and this year's recipient is Jan. And I just wanted to say, Gonzalo mentioned an incredible trajectory of his career, from having an impact of things actually implemented in hundreds of millions of actual printers, National Academy Award, not nomination, but inducted into the National Academy, multiple awards at Purdue for teaching, mentoring, research, and fellows of multiple societies. And then last night at dinner, he really put me over the top when he said he gave away 3 of his students in marriage. And I said, you cannot top that. I said, this guy can't be that good. And so, I went back and I said, I got to find something. So I said, I'm going to look at his transcript when he was a student here. I said, I'll bet I'll find something in there. I said, maybe he was a late bloomer or something. And so I thought at first he was fortunate, because in '71 the records are not electronic now. But in addition to having the greatest alumni, students and staff, we have the best staff. And I mentioned this to Debbie, and within a half hour his transcripts were on my desk. And so now I'm not sure if I'm happy or upset to say his transcripts were almost perfect. There was only a single C, and that was in physical education. So, first of all, why is he taking physical education? And then Gonzalo told me that he made him run every day at lunch. So I don't know, and he was an avid runner. So I don't know if he's trying to make up for that C, if he didn't show up for physical education or what. But that was the only shortcoming I could find in his record. So he really is that good. His work's been shown, demonstrated all over the world. In fact, I also heard a story from one of his colleagues that they were presenting internationally, and their posters were, shall we say, held on to by a customs agent, I believe it is, or someone. And so, it was for a group of them, and Jan was in charge of negotiating the release of their posters. And apparently, this, shall we say, unscrupulous individual originally wanted something like $2,000 to release the posters, and Jan talked him down to maybe $200 or something. And I don't know if he got a receipt for that. He submitted that, but apparently international negotiations are also in his resume. But really, it's just an all-around incredible career, incredible alumni, great friend of the department. And so, Xiaoming, maybe you can grab the award there, and Jen, if you can come up and a well-deserved Distinguished Achievement Award. Why don't you stay over here?
Yeah, okay.
We got
Yeah, okay, excellent.
So, in addition to that, you know, in the spirit of ECE, is very entrepreneurial discipline, I think. And every year we recognize an entrepreneurial innovation and the discipline, and quite frankly, there's a wealth of options for this. And this year's recipient of the Entrepreneurial Innovation Award is Eric Camellis. And this award is given to someone who has created an innovative business, developed a new product, brought to market a new venture, or expanded an existing business. And you know, Eric got his undergraduate and his MS degree here in 2004. And I was just in Dennis Prather's office the other day, and he pulls out from his shelf Eric's thesis. And they said, "Oh, here's his thesis that he wrote." And to be honest with you, being chair now, the only way I judge a thesis is how thick it is. And so I was pretty impressed. It was pretty thick. And until Dennis started flipping through it, I said, "Hey, wait a minute. There's a whole bunch of pages of code at the end here." And so I said, "That's the oldest trick in the book. You can't put code at the end of your thesis just to make it look thick." But nevertheless, you know, he did a great job as a student. He's co-founded and the CEO of EM Photonics, which many of you know is right up the road here. They work in high-performance computing research and commercialization, and they're looking to help certify the world's fastest computers, develop new optical devices, and looking at enhancing the video of experimental aircraft, and is also CEO of two other companies, Phase Sensitive Innovations, which is an RF technology and imaging communications company, and Luminant, which creates novel nanophotonics devices. And all three of those companies have been ranked in the top 5 R&D, federal R&D companies in Delaware, I think, for the past decade. And so that's a tremendous asset, you know, to the region, to Delaware. It says a lot about him and the company, and I think anyone who's met him knows that, I mean, he's a really great guy. He gets the best out of people. He helps coordinate things. He plays basketball, I think, up here, and he's a real team player. And he gets the best out of his basketball team, and he gets the best out of his team at the company. And so he's an all-around great guy. So Eric, if you could come up and receive our Entrepreneurial Innovation Award. And I believe the company's employ 30 people, which is really a great accomplishment. So. And then, you know, we have lots of great alumni, and one thing we like to recognize is when alumni give back. And so the next award is for Outstanding Service Award, and this year's recipient of that is Ray Sokola. You know, Ray got his undergraduate. Well, let me say the award is for someone who is through their dedicated and exemplary volunteer service illustrates the broad leadership and support of the aims and objectives of the ECE department. And you know, Ray is an alumni, graduated in '76 and had a long career with Motorola for many years, ending up as corporate VP and CTO of the $12 billion home and network business. He was an early researcher and in the cellular realm, had multiple patents, 3 Patent of the Year awards, 20 patents, was a Dan Noble Fellow, and had a great career there, and is currently vice chair of Cellport, which is looking at connectivity in cars, and he's a consultant at DTS. But he's also really given back to the department. He's been on our advisory council for multiple terms. He helped lead corporate outreach on a recent center proposal that Dennis Prather put together, and he was helpful in reaching out to a lot of corporations and putting that effort together. He's, as I mentioned, a consultant at DTS and is working on a partnership between the university and DTS. He's going to be helping mentoring some students. And also, he always asks some of the hardest questions of the dean when we have our advisory council meetings, so I appreciate that because then it makes me look good. And so, you know, he's just a great exemplary volunteer and giving back to the department. So Ray, you could come up. And then lastly, not least, but lastly, you know, we'd like to recognize our young alumni and achievements that they've made in a relatively short order after graduating. And so we have the Young Alumni Achievement Award, which is for someone that's graduated in the last 15 years. And that is someone who, you know, has exhibited outstanding technical achievement, entrepreneurship, or leadership that distinguishes them amongst their recent graduate peers. And this year's recipient is Guliang Fan. And, you know, he got his PhD here in 2001. I had the pleasure of being a member, I believe, of his dissertation committee. And since leaving here, and he was Professor Shai's student, since leaving here, he went to Oklahoma State University, where he's now a named professor. He is the Maryland Vogt Professor of Electrical and Computer Engineering. He's received more than $2 million of funding in grants. He's the PI or co-PI on 15 funded projects, and they range in the area of image processing, machine learning, pattern recognition, computer vision, and, you know, he's won a number of awards, an NSF Career Award in 2004, the Halliburton Excellence in Young Teaching Award, the Halliburton Outstanding Young Faculty Award, the IEEE OSU Outstanding Professor Award twice, quite frankly, and he's very active in the IEEE, the Professional Society. He's a associate editor of the IEEE Transactions on Image Processing, the Journal of Biomedical and Health Informatics, and on the EuroSIP Journal on Image and Video Processing. And, you know, quite frankly, I did something that no faculty member likes to have done to them. I looked him up on Rate My Professor. Right? And so, and here's a quote. There were lots of great quotes, but I looked him up and it said, "A great professor, easily one of my favorites. He genuinely cares about his students and will work hard to make sure you understand." And there's a little, if you haven't looked at Rate My Professor, if you're a faculty member, you don't want to do it. But if you're anybody else, you might want to do it. And they have these little sliders. And one of them is on helpfulness. And he was well over a 4, which was the top of the scale was a 5. So he was rated very helpful. But what's impressive is that on easiness, he was way at the bottom of the scale. So he's hard, he's fair, and he cares about his students. And that's exactly what you want out of a faculty member, of a young faculty member. He's had a great rise, and I look for more great things from him. So, Young, where is he? There he is. Congratulations. And so they're great. We have lots of other alumni, and for the students that are here, Xiaoming is going to handle the student awards for the posters today. And in the future, we look forward to transitioning those student awards to alumni awards. So Xiaoming.
So I first we want to thank all the students.
Turn the mic on.
Okay. First, we want to thank all the students who contributed posters to this year's Research Day. I also want to thank the judge panel, who is the distinguished speaker, Jan Allebach, also Ed Colley from Georgia Tech, Karen Block from Tupang, Mary Machier Machiani from Deltech, Daniel Now from University of Kentucky, Rick Taylor from IEEE, and also Daniel Now from University of Kentucky. So we fortunately have 4 sponsors for the Student Award. We have JP Morgan Chase sponsor the presenter award in the signal processing area. We have DTS sponsor the award in the nanophotonics area. ET International sponsor the Student Award in the computer area, and we also have IEEE sponsor the Women in ECE Research Award, and our department also choose undergraduate poster award from all the posters presented by undergraduate students. So the judge panel has made their decisions. So first, I want to announce the undergraduate student poster award. The winner has a poster title "Power Up Renewable Generation Battery Charging Pack" by the authors are W. Carson and H. Micholatis. So are they here? Okay. Okay, so the winning poster from the computer engineering and the lateral algebra is presented by Yuan Xue. His poster title is High-Speed Self-Adaptation in NVM-Based FPGAs Through Logic Similarity Exploitation. Yep. Come. The winning poster in the nanoelectronics, electromagnetics, and photonics area is Ramsey Hasban. His poster is X-ray characterization of group 4 epitaxy. The winning poster in the signal processing and the communication area is Angela Kojos. Her poster is coded aperture design in compressive low-dose X-ray tomosynthesis. And the Women in ECE Research Award poster is Victoria Carey. So her poster is engineered LWIR signature surfaces.
Come on up. Come on up. Doug, you
Okay.
get a picture? Yeah, come on up. Get a picture of them as a group or something. Yeah, come over here, we'll get a picture of you guys. All right, now the celebration. There's a reception upstairs, back where the posters were. So you're welcome to spend more time and talk to the winners, congratulate them, and share some time together. Thank you all.